Hello, everyone. Welcome to this talk on large scale data engineering in space exploration. Now, when we think of space, we often imagine rockets, astronauts, or faraway planets. But behind every mission is a mountain of data, and someone needs to collect it, process it, and make sense of it. That's where the data engineer comes in. We are like the pit crew for the space science. So let's dive into how we manage this cosmic flood of information. First, let's talk on the data revolution in the space exploration. Space missions today are generating more than ever before. We are talking about hundreds of terabytes every single day. To put this into perspective, imagine watching Netflix 50 years straight. That's the kind of data some missions produce. And with smarter systems, we are processing this faster and more efficiently, which is compared to older systems, we are processing this 47% better than that. We are also squeezing data like magic. Advanced compression techniques reduce the size of these huge files more than 10 times, which is like zipping a 10 gigs file down to 1 gigs before sending it across space. Now, let's talk about the data infrastructure behind these missions, right? So, when a spacecraft launches, it's like flying a smart device packed with sensors, each one collecting every single specific information. Imagine your car telling you the tire pressure, oil level, and GPS coordinates. Now, multiply that by approximately 1900 sensors working in perfect harmony in space. And because there is no garage in orbit, these systems are built to survive intense radiations and freezing temperatures from somewhere between minus 55 to 85 degrees Celsius. Now, let me walk you through a simple example of how this infrastructure works. Imagine a rocket launch. Picture the rocket like a smart delivery van loaded with hundreds of sensors, each one keeping an eye on temperature, pressure, vibration, and much more as it races through the space. As the rocket lifts off, each sensor starts collecting its own kind of information, like how hot the engine is, how much the rocket is shaking, or how fast it's going. These are like real time text messages from each sensor saying, "Here's what I'm feeling right now." All these messages are routed to what's called a remote data acquisition unit on board, and central inbox that's receiving thousands of emails per second. This unit organizes the data, filters out the noise, and compresses it to make it easier to send, just like zipping files before emailing them. Then, this cleansed and compressed data is transmitted back to Earth, specifically to a ground station, which is like the rocket's home base or an IT department. Once it arrives, it's stored, decoded, and analyzed in real time by scientists and engineers. So, in short, the sensors, acquisition unit, and then transmission, and then ground station, and then storage and analysis. This entire life cycle repeats hundreds of times per second, ensuring we never miss a heartbeat of the mission. So, what makes this entire process possible is a rugged radiation proof infrastructure. Imagine having to keep your laptop running during an earthquake, inside a volcano, and with no tech support. That's what our hardware is built for its space. Next, we're going to talk about the signal processing and how the ground support works. Think of these sensors like a music instruments in space orchestra. They are playing data notes, vibration, voltage, position at different tempos from 25 to 100 times per second. Back on Earth, our job is to make sure we hear every single note clearly. We use advanced filters to cut the noise and keep the signal clean, even when the data is flying at 4.5 million times per second. All of this is synced perfectly to the microsecond. That's like marching band performing in perfect rhythm across different continents. So let me talk on how data travels from rocket to think of rocket as an texting Earth from space. It sends the data through radio or laser signals, like sending a message through invisible waves. Sometimes a satellite in the orbit helps by acting as a postman who picks up the message and hands it off to a ground station. That ground station receives it using a huge antenna, decodes the message, checks for the error, and then stores it safely in a data center. This system makes sure we get every single piece of valuable information sent from the space. Next, we talk about the high performance computing architecture. In space, you can't afford a system crash, literally, right? So if something goes wrong, then your entire mission goes down. So we build our processors to be super reliable and incredibly efficient. They can run high-speed data operations using less energy than a regular phone charger, while surviving radiation that would fry your laptop. With triple backups and automatic error fixing, it's like having a car that can fix a flat tire before you even notice something is wrong. So next we talk about the real-time processing and how the fault management happens. Every command sent to the spacecraft must be executed quickly and correctly. No delays, no mistakes. Imagine trying to steer a remote control drone from millions of miles away. That's what we do with under 10 milliseconds of delay, faster than blinking. And if something goes wrong, the system can detect and fix the issue in less than a second. That's the space level resilience. Now let's look at the James Webb Space Telescope, our cosmic photographer. It captures up to 40 gigs of space images every day. Think of it like downloading 10,000 high resolution photos daily from a million miles away. And once it collects this gold mine of data, a smart system stores, organizes, and processes it with surgical precision, producing results within 8 to 10 hours with 98% perfection. So now let's talk about emerging technologies in the space compute. We are now using tools inspired by the future, edge computing, quantum techniques, and machine learning. Edge computing lets the spacecraft think on board instead of waiting for Earth, just like your phone using face recognition without needing the internet. We also have AI on board processing 8.7 trillion operations per second, helping space instruments make smarter decisions in real time. So, usually talking to the spacecraft isn't easy. It's like shouting across oceans and hoping your voice is clear. But we now use light beams, which is optical communication, and advanced frequencies that lets us talk up to 1.2 gigs as fast as your home Wi-Fi. The system adapts if signal is weakened, like your phone switching from 5G to 4G to stay connected. So, looking ahead, we are building a spacecraft that can think, feel, and adapt. Neural networks on board can make fast, autonomous decisions with 95% accuracy, like an astronaut's digital brain. And quantum sensors offer 20 times more precise measurements, like switching from an wall clock to an atomic clock when you need perfect timing for the deep space. And finally, the isn't just for the governments anymore. It's like booming commercially. The global space industry is worth over 420 billion with 80% driven by private companies. Think of SpaceX, Blue Origin, and startups launching satellites faster and cheaper than ever. With launching costs dropping and innovation rising, the space economy is growing at over 7% a year, and data engineering AI is at the heart of this gold rush. So, with that, thank you for joining me on this journey into the world of large scale data engineering in space, from powerful processors to fault tolerant systems and real time intelligence. The work we do behind the scenes keeps missions running, discoveries flowing, and humanity exploring further than ever before. Thank you, everyone.